There is a law in physics that has never been broken. Every experiment ever run, every reaction ever measured, every system ever studied, this law holds. Energy cannot be created or destroyed. It transforms, it moves, but the total never changes. So when someone you love dies, and their warmth fades and the room feels empty, the energy that was them didn't vanish, it went somewhere. Every joule in physics can tell you exactly where. Now I want to be very precise about this because what I'm going to walk you through is not poetry, it is not metaphor, it is not a comforting story dressed up in scientific language. Every single number I'm going to give you has been measured. Every transfer I'm going to describe has been confirmed in laboratories, in hospitals, in calorimeters, in thermal imaging studies. The universe keeps a perfect ledger, and when someone dies, that ledger does not lose a single entry. But to understand where the energy goes, you first need to understand what the energy is. And that turns out to be a much stranger story than most people realize. Because a living human body, your body right now as you listen to this, is running on roughly 80 to 100 watts of continuous power. That is the same wattage as an incandescent light bulb. You are, in the most literal sense, physics allows a 100-watt light source that has been burning continuously since the day you were born. And I haven't even told you about what your brain is doing, or what happens to the warmth in the last room someone was alive in, or why a physicist studying tropical medicine in the 1840s accidentally wrote the most profound statement anyone has ever made about loss. Let me start with the law itself. In 1818, a mathematician named Emmy Noether proved something extraordinary. She was working on abstract symmetry problems, the kind of mathematics that most people would walk past without a second glance. And she discovered that energy conservation isn't just something we observe. It isn't just a pattern we noticed. It follows mathematically from the fact that the laws of physics are the same today as they were yesterday. The technical term is time symmetry. If the equations that govern the universe don't change from one moment to the next, then there must be a quantity that is conserved. That quantity is energy. Think about what that means. Energy conservation isn't the rule someone wrote down. It isn't a principle we agreed upon because it seemed reasonable. It is woven into the structure of reality itself, a mathematical consequence of the way the universe is built. It would take a change in the fundamental architecture of existence to violate it. And in every experiment ever conducted, every nuclear reaction, every chemical process, every biological system, every star burning in every galaxy we have ever observed, it has never been violated. Not once, not by a fraction of a joule. There is a fact, or if you wish, a law governing all natural phenomena that are known to date. There is no known exception to this law. It is exact so far as we know. The law is called the conservation of energy, and it applies to everything: stars, atoms, chemical reactions, and the 80 to 100 watts running through a living human body right now. That includes your body. So let me tell you what those 100 watts actually look like from the inside. Every day you consume roughly 2,000 kilocalories of food. That is about 8,400 kilograms of chemical energy. Your body converts that energy into three things. About 60% becomes heat, pure thermal energy radiating off your skin, warming the air around you, heating every chair you sit in and every pillow you rest your head on. About 25% becomes mechanical work. Your muscles contracting, your diaphragm pulling air into your lungs, your heart beating roughly 100,000 times a day, and the remaining 15% goes to cellular maintenance, repairing DNA, building proteins, running the molecular machinery that keeps every one of your 37 trillion cells functional. You see, that is your total energy budget. 8,400 kilograms every single day allocated across heat and motion and repair with an efficiency that would embarrass most engines. Your body runs this budget relentlessly, day after day, year after year for your entire life. It never stops allocating. It never stops converting. The river of energy flowing through you right now has been flowing since the moment you took your first breath. But here's the part that amazes me. Your brain, the 3-pound organ running your consciousness right now, uses 12 to 20 watts all by itself. That's up to 20% of your entire resting energy budget consumed by an organ that makes up about 2% of your body mass. 86 billion neurons, each one maintaining a voltage difference of roughly 70 volts across its membrane, each one ready to fire an electrical signal at a moment's notice. Every thought you have, every memory you recall, every word you're processing right now, that is electricity. Real measurable physical electricity running through wet biological circuits inside your head. And those neurons are expensive. Each action potential, each individual firing of a single nerve cell costs roughly 1 billion molecules of ATP. Your brain is burning through something like 5.7 milligs of ATP every minute just to maintain those voltage gradients, just to keep the lights on. The energy cost of simply being conscious of having an inner life of being you is enormous, and every watt of it is accounted for by the first law. I want you to try something. Put your hand on your chest right now. Just rest it there. Feel the warmth. That warmth is not abstract. That is metabolic energy. Adenosine triphosphate being hydrated in your cardiac muscle 100,000 times per day, driving contractions that push blood through 60,000 m of blood vessels. The heat under your palm is measured in joules. It is as real and as quantifiable as the heat from a stove burner. And the first law of thermodynamics says those joules cannot disappear. Not when your heart is beating and not when it stops. Let that settle for a moment, because everything that follows depends on understanding this. The warmth you feel right now is energy, real energy, and the universe is keeping track of every fraction of it. Now, when someone dies, the first thing that changes, the very first measurable change, is that heat begins to leave. A living human body maintains a core temperature of roughly 37 degrees C. At that temperature, your body holds approximately 7,000 to 8,000 K of thermal energy above room temperature. That is a significant amount of heat. And the moment the heart stops, the moment metabolism ceases, that heat has nowhere to go but out. The physics of this process is governed by Newton's law of cooling. The rate of temperature change is proportional to the difference between the body's temperature and the surrounding environment. In plain terms, the body cools quickly at first, then more slowly as it approaches room temperature. The curve is exponential, steep at the beginning, flattening toward the end. Forensic scientists use exactly this equation to estimate time of death because the mathematics is that reliable. Over the course of roughly 12 to 24 hours, that thermal energy, those 7,000 to 8,000 Ks, transfers into the environment. And I want to be specific about how, because this is where it stops being abstract and becomes something you can almost see. Some of that heat leaves as infrared radiation, photons emitted from the skin surface, real photons traveling at the speed of light. Every warm object emits them. Your body is emitting them right now. Roughly 1,000 watts of infrared radiation streaming off your skin at this very moment. You can't see them. Your eyes aren't built for that wavelength. But an infrared camera would show you glowing like a lantern. When someone dies, those infrared photons keep leaving the skin as the body cools. Some of those photons are absorbed by the walls of the room, some by the furniture, some by the people standing nearby, absorbed by their clothing, their skin, their bodies. Some of those infrared photons pass through the window glass and enter the atmosphere. Some of them eventually leave the atmosphere entirely and travel into space at the speed of light, carrying that thermal energy with them forever, literally forever. Those photons will cross the galaxy. They will outlast the Earth. They will still be traveling long after our sun is burned out. The warmth of the last room someone was in, that is not a feeling. That is physics. The thermal energy is physically measurably present in the objects around them. The chair they sat in is warmer because they sat in it. That is their energy still there. Think about that. And here's where most people assume the story ends. Heat leaves the body. The room cools. But that is actually the smallest chapter in the energy story of a human life. Because the thermal energy, those 7,000 to 8,000 kilograms, is a tiny fraction of what a human body actually contains. The real energy is in the chemistry, and this is where the numbers become staggering. Your body stores enormous chemical energy in its molecular bonds. Fats alone contain roughly 120,000 kilograms. Proteins hold another 100,000. Glycogen, the quick access energy stored in your liver and muscles, adds about 2,000 more. The total chemical energy stored in a human body is equivalent to roughly 30 sticks of dynamite. That energy was accumulated over a lifetime of meals. Every breakfast, every dinner, every absent-minded snack converted into molecular bonds and woven into the physical structure of who you are. So where does all of that energy go? Through decomposition. And I know this is not a comfortable subject, but the physics is extraordinary. Bacteria break the molecular bonds that held the body together. They are not destroying energy. They are converting it. Every bond they cleave releases energy which powers their own metabolism. The bacteria grow. They divide, they produce heat. They release chemical byproducts, carbon dioxide, methane, hydrogen sulfide, ammonia, each one carrying energy away in its own molecular bonds. The energy that was stored in a human body becomes the energy that drives microbial life, soil chemistry, atmospheric processes. It enters the carbon cycle. It enters the nitrogen cycle. It becomes part of the planetary metabolism itself. Through cremation, the same energy is released more rapidly. The temperatures inside a cremation chamber reach roughly 870 to 980 degrees C. At those temperatures, molecular bonds break in minutes rather than months. The heat from cremation, that intense thermal radiation, is the stored chemical energy of every meal that person ever ate, released over the course of 2 to 3 hours. Every joule traceable, every bond accounted for. And here is where I want to bring this back to something human. Because these aren't abstract bonds in an abstract body. This is a specific person. Someone who had a kitchen and a morning routine. Every meal they cooked for you. Every piece of bread they broke at the table. Every cup of coffee in the morning with a light coming through the kitchen window. The energy from all of it was stored in their chemical bonds. woven into the fat and protein and glycogen of their body over years and decades. That energy returns to the environment. It powers bacteria. It warms the air. It enters the atmosphere as gas-carrying energy in every molecule, but it does not cease to exist. The first law forbids it. Let that sink in. You see, this is where I think people misunderstand what death is from a physics perspective. They think of it as an ending, a subtraction. Something was there and now it is gone. But that is not what the physics shows. What the physics shows is a transformation so thorough and so distributed that it looks like disappearance to human eyes. But it isn't. Every joule is present, everyone. And the story isn't finished because I haven't told you about the electricity yet. And the electrical energy of a human brain has its own story, perhaps the most precise one of all. While a brain is alive, 86 billion neurons maintain electrical gradients across their membranes. Each neuron pumps sodium ions out and potassium ions in using molecular machinery powered by ATP. The result is a voltage difference, roughly minus 70 M-volts, across every single neural membrane. That voltage is potential energy stored in the separation of charge ions ready to be released as an action potential, an electrical signal at a moment's notice. And this isn't a small amount of stored energy when you add it all up. 86 billion neurons, each maintaining a voltage gradient, each requiring constant energy input to keep those ions separated. The total potential energy stored in the ionic gradients of a single human brain, the energy of having a mind, is being maintained continuously second by second for every moment of every day of your entire conscious life. It is the most energetically expensive information processing system we have ever found in the universe. When the brain ceases to function, those ionic gradients begin to dissipate. Sodium leaks in, potassium leaks out, the voltage across each membrane drops towards zero. And the potential energy that was stored in those gradients, the energy that maintained every thought, every perception, every moment of consciousness, converts to thermal energy as the ions reach equilibrium. The last electrical activity in a dying brain, the final neural firing, produces heat, an immeasurably small amount of heat, warming the tissue by a fraction so tiny no instrument could detect it. But the energy is accounted for. Every millo, every ion, every last spark of electrical activity becomes thermal energy in the tissue that held it. And I find this extraordinary, if I'm honest, that the last thought a person ever has, whatever it is, whatever image or feeling or fragment of memory passes through their mind in that final moment, that thought is energy, and that energy does not disappear. It becomes heat. A quantity so small it vanishes into the thermal noise of the surrounding tissue, but it is there. The ledger balances. Think about that for a moment. Now I have told you about the heat. I've told you about the chemistry. I've told you about the electricity. But I have not yet given you the complete accounting. And the complete accounting is important because the first law demands it. The ledger must balance. So let me close every open line. Body heat radiated into the environment as infrared photons and conducted into surfaces in air. Chemical bonds broken by decomposition or combustion. Energy transferred to microbial metabolism. Soil chemistry. Atmospheric gases. Thermal radiation. Electrical gradients dissipated to thermal equilibrium. Potential energy converted to heat. Gravitational potential energy. A standing human being has gravitational potential energy. Mass times the acceleration due to gravity times height. For an average person, that's roughly 3,500 joules. When the body is no longer held upright, that potential energy converts to kinetic energy and then to thermal energy as the body comes to rest. Even this is accounted for. Kinetic energy of blood flow converted to thermal energy as circulation ceases and friction brings the blood to a stop. Elastic energy of tissues, tendons, ligaments, compressed cartilage, all releasing their stored mechanical energy as heat as the body relaxes. Nothing created, nothing destroyed. The ledger balances to zero. If you tracked every joule, every one that was inside someone the moment they died, you would find all of it still present in the universe, changed in form, spread across the room, the air, the sky, some of it absorbed by the people who were there, some of it radiating outward as infrared photons that will cross the atmosphere and travel through space for billions of years. But present, all of it present, and I haven't even told you the biggest number yet. You see, everything I've described so far, the heat, the chemistry, the electricity, the gravity, the kinetic energy, all of that accounts for the energy of a living, functioning system. But there is a deeper energy that has nothing to do with metabolism or temperature or electrical signaling. And it comes from Einstein, E = mc squared, the most famous equation in physics. And what it tells you is this: the rest mass of any object contains energy, an enormous amount of energy. For a 70 kilograms person, the energy contained in their mass alone is roughly 6.3 * 10^18 joules. Let me put that in perspective. That is equivalent to approximately 1,500 megatons of TNT. The largest nuclear weapon ever detonated, the Tsar bomber tested by the Soviet Union in 1961, released about 50 megatons. The mass energy of a single human body is 30 times larger than the most powerful explosion in human history. That number is almost impossible to hold in your head. 30 times the Tsar Bomber in one person in you right now. That is the energy content of your mass sitting quietly wherever you are listening to these words. And the universe is tracking every bit of it. Now, this mass energy is not released at death. It doesn't need to be because the atoms themselves are not destroyed. Not a single one. Carbon atoms, nitrogen atoms, oxygen atoms, hydrogen atoms, calcium, phosphorus, iron. Every atom that was part of a person's body remains an atom after death. The atoms redistribute into soil, into the atmosphere, into water, into other organisms. They become part of grass and rainwater and other people's lungs. But each one carries the same rest mass energy it always carried. Rearranged, yes. Redistributed, absolutely, but never diminished. The mass energy is conserved as perfectly as every other form. The atoms that were a person are still atoms, carrying the same energy in different places, in different configurations, in different systems. But nevertheless, the universe does not lose track. Think about that. Now, I want to tell you something about how we came to know all of this, because the story of energy conservation is also Hume's story, and it is one I find deeply moving for reasons that have nothing to do with physics. In the 1840s, a man named James Prescott Joule was working in Manchester, England, running meticulous experiments. He was trying to determine the exact relationship between mechanical work and heat. His apparatus was simple. A falling weight turned a paddle wheel inside a container of water, and he measured how much the water temperature rose. The measurements were agonizingly delicate. He was looking for temperature changes of fractions of a degree, tiny signals buried in thermal noise. He repeated the experiment hundreds of times, refining his technique, eliminating sources of error, building more precise thermometers. Over years of painstaking work, he proved that energy converts between forms with exact equivalence. A specific amount of mechanical work always produces the same amount of heat. Always. The ratio never changes. It is a constant of nature, as fixed and as reliable as the speed of light. Around the same time, and this is the part that gets me, a German physician named Judas Robert Mayer independently discovered the same thing, but he came at it from a completely different direction. Mayer was a ship's doctor on a voyage to the Dutch East Indies, and he noticed something peculiar. When he drew blood from sailors in the tropics, their venous blood was redder than he expected, closer in color to arterial blood. He reasoned that in a warm climate, the body extracts less oxygen from the blood because it needs to generate less heat to maintain its temperature. Less oxygen extracted means less chemical energy converted, means less heat produced. From this one observation, the color of blood in the tropics, Mayer deduced that chemical energy and heat are interconvertible and that the total must be conserved. He published his ideas in 1842, years before Joule's most precise measurements. The scientific establishment largely ignored him. He struggled for recognition. He suffered personal tragedy, the loss of 2 of his children, and spent time in a sanatorium. The recognition he deserved came only decades later when the physics community finally understood the magnitude of what he had figured out aboard that ship. Think about what happened here. One man was studying paddle wheels and falling weights in a Manchester laboratory. The other was studying the color of blood aboard a ship near Java. They were working in completely different fields, one in mechanical engineering, one in tropical medicine. They had no idea they were converging on the same truth. They had no idea they were writing the first law of thermodynamics. And they certainly had no idea, no possible way of knowing that they were writing the most powerful statement anyone could ever make about loss, because that is what the first law is. Underneath the equations, underneath the careful measurements, underneath the paddle wheels and the blood samples and the calorimeters, it is a statement about what happens to everything. That is when it changes into something else. And the answer is nothing is lost. Nothing can be lost. The universe does not permit it. The warmth of someone's hand is in the wall they last touched. The chemical energy of their body is in the earth beneath them. The infrared photons from their skin are crossing the atmosphere right now. Some of them already in space, traveling outward at 300 million meters /, carrying that thermal signature with them for as long as the universe exists. The electrical energy of their last thought is heat in the tissue that held it. Every joule that ran that 100-watt system, every joule from every meal and every breath and every heartbeat across an entire lifetime is somewhere. Everything that was them energetically is still here, transformed, dispersed, spread so thin across so many systems that no instrument could ever reassemble it, impossible to put back together. But here, every joule accounted for, every fraction of every joule accounted for. The ledger balanced to the last decimal place as it must be, as it always has been, as it always will be, for as long as the laws of physics hold. That is not metaphor. That is not comfort dressed as science. That is the first law of thermodynamics, and it has never once been wrong.